What's up, my friends? Here we are, pre-calculus. Well, actually, it's calculus, but we are learning the Intro to Derivative Unit, and in this video, we're going to talk about applications of the derivative. It's like, now that we kind of have a good understanding of derivatives, where the heck can we use this stuff? Let's get some facts straight, though. Before we move any further, we got to get a couple facts straight here. Calculus is all about change and the rate at which functions change. As x changes, f of x, y, also changes. Awesome, fantastic. That's a simple fact. Now, another fact. We can examine the rate a function changes from one point to the next. We call this the average rate of change. We can also examine the rate at which a function is changing at a specific point. We call this the instantaneous rate of change. So if we're looking at a specific point, remember that's the tangent line, and that is the instantaneous rate of change. And of course, the derivative is a formula that can find that instantaneous rate of change at any given point. This is awesome, right? So let me kind of draw a picture of this so you understand. So if I have a beautiful, wonderful function, yada, 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 yada. Okay, the average rate of change is saying, all right, here's 2 points. And what is the rate of change from one point to the next? And that would be finding the slope of that red line. Okay, awesome, great, fantastic, everything's great. But what about if we say, hey, what about at this one point? What is the instantaneous rate of change at that one point? And again, that would be the slope of the tangent line at that one point. And again, the derivative is a formula that can find the instantaneous rate of change at any given point for us. So what I want to do this video is to actually talk about some places where we can apply this stuff. So here is how we actually can find the average rate of change and the instantaneous rate of change. So these are formulas that we've already learned, right? The first lesson we kind of had was over the average rate of change, which is plugging in A for a value. So basically, average rate of change, you have 2 points, and all you're doing is finding the slope between those 2 points. That's pretty standard, no limits needed. Instantaneous rate of change, again, this is the rate of change at a specific point. This is the derivative, and this involves using the limits. So this is all stuff that we already know. So here's the deal. In this video, I'm going to focus on applications, where we could actually apply the derivative to a real-world scenario that makes some good old-fashioned sense to us. This video is not to teach you how to find derivatives, but derivatives are needed. So you will notice that when we get to a problem in this video and we find the derivative, I'm just going to instantly show you all the work. I'm not going to walk through how to find the derivative because I expect you to already know how to do it. So you are more than welcome to pause the video and examine my work to confirm in your brain how I arrived at the derivative. But I'm more focused on what can I do with that derivative in a real world problem. Finding the derivative needs to be like just, okay, got to do it. It sucks. Might take a couple steps, but I got to do it. And I'm not going to waste time in this video showing you how to find the derivative because I expect you to know already how to do that. I'll show you the work, but it's up to you to pause to look at that work if you want. All right, so what are some real-world applications? So basically, remember, calculus is all about change. So what types of things change in the real world? Well, here are 2 examples. The volume of a cube changes as its dimensions change. So remember, a cube has all equal sides and equal height, length, width, everything. Everything is the same. So imagine if I called the dimensions x. So x by x by x, then the volume would be x cubed. And imagine if I labeled the volume as f of x, right? So that means the output, the volume, is f of x, and the input is x, which is the length of the dimensions, and now, of course, the volume would equal x cubed. So here's a function that, yes, without the real-world application, just looks like a brand standard generic function x cubed, but now it actually has meaning. F of x is the volume of a cube, and x is the dimensions of that cube, hence x cubed equals that volume. And again, it makes sense if the dimension x gets bigger, the volume changes, and it also gets bigger. If I make the dimensions x smaller, the volume changes and gets smaller. So as the dimension x changes, so does the volume f of x. Another example is the surface area of a sphere. Now, it's kind of hard to draw a 3D sphere, but I'm going to do my best. So a sphere kind of looks like, so if I do this, I don't know, very bad, right? But kind of looks like this 3D sphere, right? And what we know about this 3D sphere is that the surface area, which is like if you were to paint the sphere, the outside of the sphere, that's the surface area. As the radius changes, that surface area gets bigger or smaller. If the radius gets bigger, surface area changes and gets bigger. Radius gets smaller, surface area changes and gets smaller. So maybe I'm going to let the radius be my input because that determines the surface area. So I'll call that x, and I'll call the surface area f of x. So I have a function where you plug in x, the radius, and you get out the surface area. So these are going to be like functions, but they now actually represent some real-world applications. So let's take a deep dive at this first example. So this first example is going back to that volume of a cube. And of course, I'm going to let x equal that equal length, width, and height. And obviously, if I multiply the length, the width times the height, I get the volume of the cube. So hence, x cubed represents the volume of a cube. So f of x represents my volume, and x represents the dimensions. Again, if you want to draw a little picture, go ahead and do so. I'm not too great at drawing cubes, but those are my dimensions. All, again, length, width, and height are all x. So this wants me to find the average rate of change. Remember, average rate of change is not a derivative. This is just simply finding the slope between 2 points. So if I think of a cube, and if it starts off with a 5-inch value for x, right? If the volume, or excuse me, if x is 5, then the volume would be 5 cubed, which would be 125. So input is the length, width, and height of the cube, and the output is the volume 125. But if I increase by 0.1, if I just add 0.1 to my dimensions, I'm going to get a new volume. So 5.1 comma, and again, my new volume would be 5.1 cubed, which is 132.651. So if I say, okay, so from this cube with a dimension of 5 to the second cube with the dimension of 5.1, how did the volume change? Well, I'm basically finding the slope between these 2 points. So I'm going to take f of 5.1, which I already know is plugging 5.1 in, 132.651, and subtracting f of 5, the second volume, or I'm sorry, the original volume of 125, all divided by, again, my x's went from 5.1 down to 5. So again, in my numerator would be 132.651 minus 125. That's 7.651. All divided by 5.1 minus 5 is 0.1. So once again, right, I'm finding the average rate of change. My denominator is how the volume changed. Well, excuse me. The numerator is how the volume changed. The denominator is how the dimensions changed. So again, now if I simply divide by 0.1, I get 76.51. So that is cubic inches per 1 inch. So every time the cube gets 1 inch bigger in dimension, its volume changes by 76.51 cubic inches, right? So again, slope is rate of change. Rate of change is like speed. So it's saying, all right, as this cube gets bigger, how fast is its volume increasing? So for every 1 inch that the cube gets bigger, the volume increases by 76.51 inches per cube. Now again, that's going from a dimension of 5 to a dimension of 5.1. But another question I could ask you is, what is the instantaneous rate of change at a moment when the dimension is 5? So if I stop with a cube that has dimension of 5, at that instant, what is the instantaneous rate of change? And of course, instantaneous rate of change requires the derivative. So if I want to find the rate of change, the instantaneous rate of change at a value of 5, I need to first find the derivative of this function. And here is the work to find the derivative of that function. Once again, pause the video if you need to. This is stuff that we've already learned. I'm not going to review this, but painstaking as it was, I went through every single step showing you how to find the derivative. And I ended up getting a derivative of 3x squared. So if I want to find the instantaneous rate of change when the dimension of that cube is 5 inches, all I have to do is plug 5 into the derivative, because remember, the derivative is a formula to find the slope, aka rate of change, at any single value. So I'm just going to plug in 3 times 5 squared. 5 squared is 25. 25 times 3 is 75. So at the instant where the cube has a dimension of 5 inches, its speed, right, its rate of change is 75 cubic inches per 1 inch. So pretty easy there. But again, I sped through the derivative because you should already know how to do that derivative work. But this is a pretty good derivative problem. Take a look at all my work there. I really spent a lot of good time with that work. But again, if you're asked about instantaneous rate of change, all you need is the derivative. Do the work to find the derivative and then plug in that one value to get your rate of change. All right, let's look at a second problem here. This is the one dealing with the surface area of a sphere. So this is a formula to find the surface area of a sphere. So I'm calling the surface area of the sphere f of x. So I'll call that SA. That's the surface area of the sphere. And the surface area of a sphere depends upon the radius, which I am calling x. So 4 pi times x squared is a formula where you will get the surface area based on the radius x of the sphere. Bigger radius, bigger sphere, bigger surface area. And this says, what's the instantaneous rate of change at a radius of 6 inches? So if you think about this sphere being really small and growing and growing and growing and growing and growing, it's constantly changing. At the moment that sphere has a radius of 6 inches, what was its rate of change? Well, to find that instantaneously, I need the derivative. So on this next slide here is the work to find the derivative of this function, 4 pi x squared. And again, some really good solid work there. I'd really encourage you to pause the video and examine that work. But I did end with a derivative of 8 pi x. So what is the instantaneous rate of change when the radius x equals 6? Well, all I got to do is plug 6 into the derivative. 8 pi times 6. That's going to be 48 pi. And if you're interested in getting a decimal, I'd be okay with you actually figuring out 48 pi is approximately 150.796. And that's going to be 796. That's going to be inches squared per 1 inch. So as the radius gets bigger and bigger and bigger by 1 inch, the volume, or not the volume, oh my gosh, I'm sorry. The surface area gets bigger by 150.796 square inches at that moment. So if you think about a sphere, every time it gets bigger, even by a smidgen, its surface area is getting bigger. And at the moment when it has a 6-inch radius, the instantaneous rate of change at that moment is 150.796, or again, about 48 pi. So again, these problems are actually super fast once you have the derivative. But listen, finding that derivative definitely takes time. All right, what are some more uses of derivatives? What are some other places in the world where things change? Well, here's 3 more. The distance a car travels changes as time changes. Okay, so as time changes, we can call time t. So as the time ticks by, a car is moving, the distance that car moves has changed. When you throw a ball into the air, the distance that ball is from the ground changes as time changes. So once again, if we call t time, if I throw a ball into the air, as the seconds tick away, the height that that ball is from the ground changes. If I take a ping pong ball and I roll it on the ground, the distance the ball was from the start changes as time changes. So if I take a ping pong ball and I put it down on the ground, and that would be like position 0, and I start rolling it. As the time ticks away, the distance that ball is from me is growing. 1 foot, 2 foot, 3 feet, 5 feet, 7 feet, 20 feet, as that ball keeps rolling and rolling and rolling. So again, these are other examples where as something changes, in these 3 examples, as time changes, something else, the distance a car travels changes, the distance a ball is from the ground changes, or the distance a ping pong ball is from the start changes. Now, these types of problems are known as position functions. The previous 3 examples I just went over are position functions. A position function is highly used in calculus. I can't stress them enough. We're going to use them a ton. A position function is a function that specifically looks at the position of an object after a time t. So we're no longer going to use x. I mean, you could use x, but I'm going to use t for time. So in a position function, the input is a time, seconds, minutes, hours, whatever. You got to read the problem. And the output is the position of an object. And again, that could be the position in terms of how many feet a ball is from the ground or how many meters a car is horizontally from where it started. But FYI, real quick, oftentimes with position equations or position functions, they're labeled S of t. Now, we're used to f of x, but S of t is just something that mathematicians typically use for position functions. So S of t is just saying, hey, after t seconds, whatever, minutes, hours, after time t, what is the current position? So S of t, why they use S, I'm not really sure, but S of t is just the position that that object is. All right, so let's talk about these problems, right? Every problem that we kind of looked at here, the three examples, we were all looking at distance versus time. Now, hold up. We have a word for the rate of change of a moving object, right? When an object is moving, you throw a ball in the air, you roll a ping pong ball, you push a car. When an object is moving, we say that that object has speed. Speed is just a fancy word for rate of change, right? If you're driving in a car at 30 miles per hour, your rate of change is literally 30 miles per hour. That is a rate of change. So, but actually in this class, we're not going to call it speed. We're going to call it velocity. If you've taken physics, you know what I'm talking about here. But velocity is speed with direction, which is actually better. So a ball with a velocity of negative 25 feet per second, that's a ball that's dropping. That's a ball that was in the air and it's dropping down. The negative is what's telling me that it's going down. The 25 is its speed, the 25 feet per second. So if a ball has a velocity of positive 25 feet per second, that means the ball is moving up. Like maybe I had a cannonball and I projected this ball up into the air and it's going up. That's the positive. So velocity is nothing more than speed with direction, positive or negative. But again, like listen, right? This entire unit, calculus, is all about rate of change. And speed, now velocity, is a great example of a rate of change. So let's dive into this a little bit deeper. So we know about average velocity, right? Average speed. So the average speed is very simple. We're saying, okay, if you start at time t and you end a little bit later, t plus h, right? So if we have a ball and we start that ball at time t and then we allow that ball to roll for, I don't know, h seconds, then its new time at the end would be t plus h. Well, this S of t is its original position. Maybe we could call that 0, or maybe if this was the starting line right here, then it's then here maybe it's I don't know, maybe it's 5 feet from the start, whatever. But S of t is just its position at t seconds. And then S of t plus h would be its new position after we have allowed time to pass by. So the average velocity would be looking at simply the rate of change from the end to the beginning. So listen, this should sound very familiar. The numerator is the change in distance. So how much did our distance change? Oh, the ball traveled 10 feet. And then we divide that by the time it took to travel 10 feet. So again, this is speed, right? Miles per hour. How many miles did your car go per 1 hour? So again, average velocity is simply looking at the change from one position to another. That's average velocity. That's taking our ending position, which is known as S of t plus h, right, our ending position, and subtracting our initial position, which is S of t. Again, don't let the S confuse you. Remember, S of t is just what we typically call the position. And then we're going to divide it by how much time has passed. And if we're going from t to t plus h, that is h. Now, again, that formula should look very familiar because, of course, that is the average rate of change formula. All I'm doing is using S instead of F. What's the difference, right? And then, of course, we have instantaneous velocity. So the instantaneous velocity of an object is the object's rate of change at a specific time. When that time is t, we could find that object's single velocity at that one instant. And of course, this requires the derivative, right? Because think about the connection here. The derivative is a formula to find the slope of a tangent line. Well, slope is a fancy word for rate of change. Rate of change is even a fancier word, or excuse me, velocity is even a fancier word for rate of change. So to find the velocity of an object at a specific time, you need the derivative, which is, of course, the limit of h as h approaches 0. So again, let me kind of draw a picture to really kind of sum this together. So imagine I'm standing here. I'm a beautiful person. I'm standing on the ground, and I launch a ball, maybe a tennis ball, up into the air, and then gravity kicks in, and that ball comes back down, splat onto the ground. Well, if I say, okay, let's pause time right here and right here, and I say, okay, from this time, let's call that time 1, to this second time, we'll call that time 2, what was the average rate of change? From this position to this position, what was the average rate of change? And again, there's of course going to be a position function where you plug the time in and you get the position. And again, the position would be the height the ball is from the ground. So again, the average velocity would simply be the change from one position to another. That's easy. But if I said, okay, let's pause time right here. At this one specific time right here, what is that ball's instantaneous velocity? So that would be finding the rate of change of that tangent line. And of course, I hope you would understand the velocity should be negative because at this position, the ball is on its way back down to Earth. So again, that's the idea, right? All we want to do is use the position equation to tell me where the ball's at, and then I could use the derivative to tell me the instantaneous velocity. So let's look at an example. This may be a little bit confusing right now, but after we look at an example, it should make a lot of sense. All right, so a ball is thrown straight up from a rooftop 175 feet high with an initial velocity of 52 feet per second. So just to kind of draw I'm not great at drawing. So here is a rooftop, and somebody's standing on top of this roof, and they throw a ball up into the air, and that ball is going to eventually come back down and hit the ground. But that ball was thrown with an initial thrust of 52 feet per second, and that ball is going to continue to go up, 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 up until it reaches its max and comes back down. And this right here is an example of a position equation or position function. This will tell you the height of the ball after t seconds. You plug in t, you will get out the height of the ball from the ground. All right, now, I actually went ahead and graphed the function so you could see like a really good picture of it. So here's a beautiful picture of this function. Right here is the start at the top of the building, 175 feet above the ground. You actually don't need this part of the function because that would be a negative time, and you can't have negative time in the real world. So here's that ball being thrown up into the air, and as time ticks away, that ball reaches its max, and as time continues to tick away, that ball comes back down to the ground. All right, so what could I ask you? Well, one question I could ask you is what is the instantaneous velocity of the ball 2 seconds after it's thrown? So if we go back to the graph here and we look at, okay, where do I see a time of 2? So right here is a time of 2. So at 2 seconds right here, when the ball stops, if I pause time right here, what is the instantaneous rate of change of the ball at 2 seconds? Well, to find the instantaneous rate of change, that is the velocity, that is the rate of change, and of course, that is slope. So to find the slope at any given point, I need the derivative. So voila, here is my work to find the derivative of this function. Once again, this video is not about teaching you how to find a derivative. I expect you to know already to do that. So I encourage you to pause the video right now and follow my very meticulous, look how beautiful my handwriting is as I typed out how to find the derivative. But at the end of the day, the derivative of this function, hopefully you take the time to figure it out, the derivative is negative 32t plus 52. So if I want to find the instantaneous velocity when the time is paused at 2 seconds, all I have to do is plug 2 into the derivative, which will tell me the slope, rate of change, velocity, all meaning the same thing, at 2 seconds. So I get negative 32 times 2 plus 52. And again, if you need to use a calculator, feel free. Negative 32 times 2 plus 52 is negative 12. So that's negative 12 feet per second. And now notice it's negative. And we knew it was going to be negative because we saw in the graph at 2 seconds, the ball is on its way down. It's barely, but it is off its peak. It's on its way down. So at that time, the ball is moving negative 12 feet per second. All right, makes sense. And I hope you guys know gravity, right? As that ball continues to go towards the earth, gravity will make that ball speed up. So this leads me to another question. And that other question is this. This is a really good question. What is the instantaneous velocity of the ball when it makes impact with the ground? So when that ball makes impact with the ground, what is its instantaneous velocity? Well, here's what I know. I know that instantaneous velocity is instantaneous rate of change, which is instantaneous slope, which is the derivative. And I already know the derivative of this function, I already showed all the work for it, is negative 32t plus 52. That should be a t right here, not an x. Sorry, I get so used to writing x's. So this is a formula that can find the instantaneous rate of change, the instantaneous velocity. Now, the only thing I need to use this derivative is I need a time. So what I need to figure out is what is the time when the ball impacts the ground. So if I go back to my graph here, I'm looking for this right here. What is the time when the ball smacks into the ground right here? And it does look to be a little bit more than 5 seconds. So there's 2 ways you can figure out that time, because I need to know exactly what that time is. Once I know that time, I can plug it into the derivative to get the velocity at that moment. Well, let's see here. One thing I could do is I could graph this in Desmos. If you go to Desmos, graph the position function, all you got to do is click on this number and you will get the x value. And that x value right there is, again, like I said, it's going to be 5 point something. But if you're looking to find a way to do that work by hand, remember, all you got to do is some good old-fashioned algebra. So again, when it hits the ground, that's a position of 0. So if I turn or if I set the position function equal to 0 and solve, right? When it hits the ground, its position, the distance above the ground, is 0. So if I set the function equal to 0 and solve, I will get the time. Now again, here is the work for that. Of course, I had to use the quadratic formula because I did not think that this quadratic was factorable. So I went ahead, this has nothing to do with derivatives, this is just good old-fashioned algebra. I went ahead and I used the quadratic formula. Pause and look at my work if you need to. I used the quadratic formula to figure out what the time is when the function equals 0. And I actually got 2 answers. I got 5.310, which makes sense according to the graph, and I also got negative 2.060. Because remember, quadratics have 2 solutions. But I'm going to ignore the negative solution because negative time is impossible in the real world. So this is the time that it takes for the ball to hit the ground, 5.310. If you're looking to not do all this ugly quadratic formula work, I highly encourage you to simply type the position function into Desmos and click on the x-intercept and you will see 5.310. So now to find the instantaneous velocity when that ball hits the ground, all I really have to do is plug that time into my derivative. So if I take 5.310 and I plug it into the derivative, or f prime of x, I get negative 32 times 5.310 plus 52. Sorry, I'm a little bit of a headache here. So negative 32 times 5.310 plus 52 is a instantaneous velocity of negative 117.92 feet per second. So why is it negative? Because the ball was coming down when it hit the ground. It wasn't coming up, it was coming down. And it's moving pretty quick because gravity really starts to, when you throw something up, the reason why it comes down is because of gravity. And as that ball starts to come down, down and down, it's picking up speed, it's picking up velocity. And when that ball crashes and boom and makes impact with the ground, it was traveling at a negative 117.92 feet per second. And again, this problem is very, very simple to understand as long as you say, hey, it's worth taking the time to find the derivative. So I found the derivative of the function. I got negative 32 plus 52. The derivative can be used to find the instantaneous velocity at any moment. Anytime I stop upon this graph, I can find the instantaneous velocity. All I have to do is plug the time in to the function, plug the time into the derivative. So it's really important that you guys understand that these position functions have two things. They have s of t, that's the position function. You plug in time, you get the height above the ground. And then we have the derivative, which I guess instead of calling f prime, I should call it s prime. Doesn't really matter. Anytime you see that little accent mark, you're talking about a derivative. So the derivative, you plug in t, you get the velocity. So let's talk about 3, for example, right? If I say, all right, at 3 seconds, right here, at 3 seconds, how high am I above the ground? Well, you simply plug 3 into the original position function, and you'll get the height above the ground. Looks to be maybe about 180 feet, maybe somewhere around there. If I plug 3 into the derivative, I get the speed. No. The velocity of this ball at that instant, at that 3-second instant. How fast was that ball moving? So position function gives me the height above the ground. Derivative of that function gives me the velocity, the rate of change, which is the slope. So yes, go back to the definition of derivative. The derivative is the formula to find the slope of a tangent line at any given point. But slope can be looked at as rate of change. Rate of change can be looked at as the velocity if you're an object that is moving. All right, so these are great examples of where derivatives are used in the real world, and they are very powerful to giving us some awesome information about objects that are in motion. All right, hopefully you guys understood. We'll look at some more examples later on. Love you.